So the overall sort of discussion outline, we're going to talk through really briefly definitions. McKinley just gave us that definition, so we can kind of walk through that pretty fast. And then I'm going to spend the bulk of this conversation walking you through concrete examples. So these vulnerabilities exist in the wild, and some of them are unpatched still. So the examples I'm giving you, a couple of them are sanitized. But it'll give you a sense for how to find them and why they exist today. And then we'll talk a little bit also about the spectrum of severity. There's a lot of, obviously these vulnerabilities can be catastrophic, but often they're known and just unpatched because they're considered to be nuisances more than anything else. And then we'll also do a little bit of a walkthrough of how a malicious actor, as unsophisticated as a script kiddie to someone who has more capabilities, might actually go about the process of trying to identify and exploit these vulnerabilities, to give you a sense of the process people go through to find these things. And then part of the conversation is also focused on new challenges. So especially with the emergence of LLMs, how are more sophisticated entities applying those technologies to exploit these vulnerabilities en masse? And then finally, mitigations. Perfect. So the core of this conversation is going to be focused on BOLA and BFLA. BOLA, as McKinley just described, is a set of vulnerabilities associated with object-level access that should be unauthorized for a particular user. Often this relates, as McKinley mentioned, to modifications of a call payload where an ID or some other type of access variable is modified, and rather than that call being blocked, the server responds with unauthorized data. Broken Function Level Authorization gives the unauthorized user access to functions that they shouldn't have privileges for. And then there's a whole host of other OWASP top 10 API vulnerabilities that are very closely related. I'll really briefly touch on unrestricted access, unrestricted resource consumption, just because that tends to be very common. But we're going to focus primarily on the first two. And you may be thinking, this kind of came up in the Q&A. It's 2024. Who is writing an API that has these types of very obvious vulnerabilities? Well, the truth is, all of our web apps are built off of an API infrastructure, sort of client-server architecture that requires API endpoints for the products to work. And these API endpoints are different than what we traditionally think of as SDKs. They're not developer-facing. They're not anticipated to be used by anyone other than the valid client front end. And so there's an implicit amount of trust in these APIs that the calls made to them, made to these endpoints, are going to be bounded by the behaviors allowed by the UI, by the client front end. And that implicit trust is what an unauthorized malicious actor can abuse. So here's a really simple example on the left-hand side. If you go to the Twitter homepage, it will kick off something like 250 different calls almost simultaneously to different endpoints that return data that populates your screen, that personalizes your experience of Twitter. If you kind of look at this one very specific tweet, this is the first tweet that just comes up in this home feed refresh. You can see it says, significant progress in AI and robotics this week, blah, 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 blah. That string of text is actually coming from an API call that you can see on the right-hand side in very small font. The call itself is to an endpoint called home timeline, and the response object includes this key variable of full text, and the value of that key is the tweet that we see. And so you have these endpoints that are returning for you very nice structured objects, and the calls to them are the things that we're going to be talking about, how they can be abused. Okay, let's get into it. So concrete examples. The first example I'm going to share with you is an example that impacts an electronic health record system. This is a piece of software used by physicians' practices to manage their patient records, their encounter data, claims data, basically every piece of sensitive information related to a healthcare practice. This particular EHR is used by tens of thousands of practices in the United States, treating millions of patients. This EHR has a really nice sort of portal for physicians where they can log in, go to a patient page, and see all of the claims associated with that patient. And there's a nice, beautiful little button that says print. And if you click that button, it allows the practice manager to be able to print all of the claims associated with that patient so that the patient can get them in a printout so they can see what the insurance paid, what what they're obligated for. And that printout, can be sent to other physicians, to insurers, all sort of practical healthcare purposes. Now, what happens when you click that button is the client device sends a request to an endpoint. And this endpoint is this like printer microservice at the EHR. That printer microservice expects within the call payload, which you can kind of see a sanitized version of on the right-hand side, expects in that call payload to read a variable called claim ID. And as you can kind of see here, that claim ID happens to be a very clean integer. It's like a very simple value. That printer microservice takes that claim ID and looks up against the EHR database all of the claims associated with that claim ID. The data comes back from the database. The printer microservice takes all that data, puts it into a nice PDF template, sends it back to the client device. Now, the printer microservice authenticates that that request is valid. It's coming with a valid session token. The user is logged in with valid credentials. But nowhere along this path does the printer microservice nor the database ensure that the claim ID that's being requested in that call payload is valid for that particular user. And so a malicious actor can take valid credentials for a practice manager and start guessing at claim IDs for unrelated claims and unrelated patients. And in fact, what makes this especially pernicious is that this claim ID is very guessable. It's a clean integer. And if you are looking at kind of the sequence of them, you'll notice that they just increment by 1. And it's a global variable across all practices, across all patient claims. And so all you need to do to get all claims that are ever processed by this EHR is start with the latest one and decrement back 1 by 1. And this is a type of vulnerability that can obviously give you access to very sensitive patient information that no one should, other than patients and physicians, have access to. Okay, hopefully no one's too terrified yet. Next, we're going to talk about broken function level authorization. So this is a different type of vulnerability related to a different EHR. I happen to work with a lot of different EHRs. This EHR has a really nice portal where physicians can log in and edit encounter details for every appointment that their patients have. They have these 2 nice little buttons in their UI. One button says edit, one button says delete. And those buttons, when pressed, send a request to an endpoint that processes that effective administrative action, which is updating the record for that encounter or deleting that encounter. Now, patients also have a separate portal that they can log into to view encounters related to their own visits to a practice. What happens is when the patient logs in and goes to this particular portal, they're actually calling the same endpoint that's used to edit or delete records for these encounters. The difference is the patient client makes a GET request to that endpoint and doesn't include these additional parameters that are in the payload. But what's really interesting is if a malicious actor knew about how to reconstruct that payload or could guess at some of these actions, they could modify that payload and have this function called to delete or modify these encounter records and won't be stopped by the server. There's an authorization flaw in there. What makes this particular vulnerability also bad is that it's coupled with broken object level authorization. Patients and physicians are able to access other records if they modify the encounter ID. The encounter ID happens to be less guessable for this EHR, which is one of the really strong preventative measures for trying to block these types of vulnerabilities and attacks. But it still doesn't prevent someone who has more compute resources, more time, more knowledge from being able to exact a lot of damage across these physician practices. And then really quickly, just touching on unrestricted resource consumption, this is an issue that comes up when often client front ends make requests to APIs that explicitly in the call dictate how much data or how much work needs to be done by the server side. So this is a very simple example where a call is made. If you have a product that has an infinite scroll feed, often when you scroll to the end of the feed, it'll trigger a call to an endpoint to get additional content. And in that call, you typically have an explicit reference for how many rows of data or amount of data to return back. Here in this example, this is a knowledge database. It's an expert network product called TGIS. They've patched this since it's been known, but effectively they have a library of private company transcripts that they sell for thousands of dollars a year as an annual subscription. If you're a user of TGIS, you can log in and read as many transcripts as you want. Their assumption is that as a human, you're not going to be able to consume tens of thousands of these transcripts in a given year. But if you were a malicious actor, you can go to this specific call that would only return 20 transcripts at a time in their infinite feed. And instead of 20, request 20,000. As long as the endpoint doesn't time out or fall over, you will get those transcripts. And for these types of products, often they have a free trial. So you can get valid credentials to be able to log in and request this data or see this data and effectively extract all the value of the product before becoming a paid user. Unintended actions, effectively, that you as a backend engineer might want to mitigate against. Okay. So how do people think about these types of vulnerabilities? Frankly, a lot of the time, these vulnerabilities are known to the product owners, and they leave them unpatched for a prolonged period of time. On one end of the spectrum, sometimes they're thought of as being kind of a net benefit for the company, which is kind of crazy to think about. If you have a product and other people are trying to programmatically interact with your front-end APIs in an unauthorized way, it typically means that they want to integrate with your product but don't have access to a dedicated developer SDK. And so you might want to let them just do their integration through this unauthorized format because it avoids you having to dedicate engineering resources to stand up a dedicated, metered, authorized developer portal for them to access instead. And it kind of gives you the liberty at some point to either sue them or effectively block their access to these types of front-end integrations at a business-critical moment for negotiation purposes. It's come up a couple of times. We'll talk about an example for a fintech solution a little bit later. And then on the low end of the spectrum, in terms of people who consider these vulnerabilities actually harmful, they're often considered nuisances. They might be considered resource consumers, or potentially a source of lost revenue. So in the example of TGIS, that's a pretty big source of lost revenue if someone actually exploited that vulnerability. But often, a product may have a developer SDK. It may be a product that requires you to subscribe to it as a developer to be able to access it. And so if you integrate through the front end and skip the SDK, you're kind of losing that revenue as a company, but maybe it's not that important to you anyway. Where things get more sensitive and where people start to act more relates to product integrity violations. So privacy violations where data is being leaked about users that shouldn't be authorized for view by a particular set of credentials. And this becomes especially pertinent when obviously there's a threat of that leak or vulnerability becoming publicly known. And where teams I've seen react much more quickly relate to where these vulnerabilities effectively cause the product to break. So you're finding microservices failing because someone's exploiting this vulnerability, or you're finding that there is a severe product issue. For example, the data deletion, data modification vulnerability that we talked about before. If that starts to happen and data is disappearing from these electronic health record systems, that's when obviously it's going to have a significant business impact and companies are going to care about rectifying those vulnerabilities very quickly. But I think the point here is just there's a spectrum, and often it's not considered high urgency to act. Now, what kind of is impacting the sort of spectrum of severity here is that on one hand, you have a lot of modern web frameworks that default to exposing endpoints even when developers don't anticipate them. So this tweet on the left-hand side points out a Next.js flaw, or not flaw, but a challenge for developers that they need to be aware of, where if you're setting configs and you establish a use server config within your Next.js app, by default, every exported function is going to have a publicly available endpoint in your app. And you might not be aware that that's possible. And some of those functions, even though they're not called within your client, are going to have endpoints open for them. And so if there's a function that you don't actually even have reference in your client front end, on the back end, you might not even be thinking about security because you think of that as a private pure function. But these sort of configs are becoming a really big challenge for modern web apps. On the right-hand side, I found this tweet really funny. This guy tweeted, I was trying to book a doctor's appointment earlier, and the form was broken, so I spoofed via curl and was able to book. That's awesome for him, but I wonder, why was that form broken? Was the practice closed? Are they not accepting your insurance? So users are becoming savvy and starting to interact with products programmatically in ways that we think the UI is actually blocking them from doing. Okay. So now we're going to put on our black hats and kind of start to think like how a malicious actor would go about identifying and exploiting these types of vulnerabilities. The goal here being to hopefully give us tools and a sense of intuition for how to protect against them. So the first thing that a malicious actor will do is get a set of credentials that are valid. So they will maybe get a trial license, they might subscribe for a product, they might find someone else's user information and log into the product. And they'll open the sort of, they'll start logging and monitoring network requests that are being made by the client front end as they're interacting with the product. So you'll click around, you'll see, when you scroll to the bottom of the feed, what's the call that gets made. When you go to your settings page and try to change your password or view your password if that's available in your portal, what's the call that's made to the endpoint to return that data. And you start to figure out kind of what all of the calls are, what are the different endpoints that are accessible through the client front end. The next step is really simple. You start looking at some of the calls that seem to be highest priority, maybe returning interesting information or executing interesting actions, and you can replay them. You just copy them as curl commands, put them in your terminal, or however you want to execute the code, and see whether or not those calls are responding with valid responses. Once you do that and you get valid responses, what a malicious actor will do is start removing specific things like headers that might be unique identifiers. They might try to test if there's a CSRF token requested. They might test deleting that CSRF token or changing it to see if there's valid authentication of that CSRF token. They might also try to see if there's a way that they can break the authentication protocol. For example, they can sort of see if, for example, if there's a session token, that session token is being validated just based on its sort of encrypted format. So once you decrypt it, it says it should expire at this time. Sometimes some of the APIs that I've come across just validate based on that rather than actually knowing if that particular session token is valid for a credentialed user. And then once you kind of have a sense of what you can get away with, it'll dictate for you how much authentication you have to go through to be able to access the unauthorized elements of the API. And then the last step is you start to make modifications to the API calls. You start to guess at, okay, this is the payload. It has this variable called count. Instead of requesting 20, we're going to request 2,000 and see if that generates a valid response for you. This process is very tedious. It is pretty manual. And the more semantic awareness you have, the better you can be at it. So it often helps if you understand the underlying product or context that users or developers have when they're building it. Now, all of this changes in the context of LLMs. This is sort of like the new nightmare. What used to be a very manual process can be programmatically driven by prompting an LLM to give you valid guesses for either endpoints or call parameters based on what you know to be valid formats for API endpoints. So this is kind of a tough thing to read, but on the left-hand side is an example of an endpoint that is known to be valid for a particular API, get schedule list. Now, instead of me sitting down and guessing, okay, what are other potential endpoints that may not be visible in my front end but could return valuable information, I can just prompt an LLM to effectively hallucinate a bunch of different options and programmatically just hammer the network to see if any of those endpoints return valid responses. You can do the same thing with the parameters of the call. So you can feed, I know that this particular endpoint or this particular product has this weird sort of like data payload expectation where their key values called, for example, include resource, and the value, if it's set to true, responds with a resource object. Okay, well, what happens if we start guessing at, let's say this is an EHR or health software, health product software, Maybe it has something called include patient name. Maybe it has something called include SSN for social security number, just to see what other types of objects we can potentially access. It gets really dicey when you can programmatically create all of these guesses and just hammer the network and just effectively fuzz these products to see what responses you can validly get back. Now, it's not just malicious actors who are trying to programmatically integrate through these front-end APIs. There are a lot of people who've built what they consider to be good products that have user value and societal value off of these types of integrations. A really good legacy example is a company called Plaid. So Plaid is a piece of fintech infrastructure that allows developers through one standard SDK to be able to access bank portals and banking information on behalf of users across thousands of different US banks. And the way Plaid literally got started was they started screen scraping. They had an iframe. So you would say, I have a Bank of America account. And they would, in that iframe, ask you to log into Bank of America. And you would think that you were still on the Plaid portal. You were maybe giving your credentials to Plaid in a protected way. But what they were effectively just doing was through that iframe, logging into Bank of America on your behalf, and then pulling your checking account balance and pulling sort of the routing information for your account so they could initiate ACH requests. They did this in a very manual and brittle way for thousands of banks, and every time those endpoints or potentially even the UIs for instances where they were just literally doing screen scraping, every time those changed, they would have to manually go back and rectify their integrations. It's very expensive, but for this particular use case, it ended up being valuable enough to manually do this work. It's the product that sort of powers a lot of financial products that require an integration with your bank account. Now, there are a bunch of different companies, including foundation model companies, that are trying to create new user experiences for web products by effectively automating this process and making a generalist product for integrating through front-end APIs. Happy to talk about this, but it kind of looks like a Good Samaritan version of abusing APIs that are undocumented for external use and technically against terms of service to be programmatically interacting with. These sort of front-end APIs just meant for the client front-end. Okay, mitigations. So what can you do? Obviously, you can always just turn off your servers. But short of that, the first step, as McKinley mentioned, one of the steps McKinley mentioned, first step I think, is to begin monitoring. Monitoring just simply means try to identify the scale and scope of these authorization flaws within your products. Some of the simple ways to do this is to look at effectively, try to use cookies or session tokens, whatever is your authentication format, to map back to a single account and try to identify users that are responsible for large volumes of requests. Look for requests that for some reason happen to have significant resource demands. If someone's requesting 20,000 rows when they should be requesting 20, it will show up somewhere in your resource footprint. Look for failed requests. The path to identifying authorization failures is a lot of failed requests are sent to your servers through typically authenticated credentialed users' client calls. And then look for unnatural patterns. What this means is that your client front end, when you load the Twitter homepage again, for example, it's not only going to call the home timeline endpoint, it's also going to call this like hot topics endpoint to populate this modal on the side, or your number of followers endpoint. You should have all of those endpoints naturally occurring if a user is interacting with your UI in the way that you intend for them to. What you'll start to notice with these programmatic abusers is they will kind of hammer the endpoints that they care about and ignore the rest. It's very difficult to actually write rules to identify this, but ML engines are very effective at identifying these types of unnatural patterns. So collecting this data can allow you to sort of train those models to identify very quickly. Next up is to test. And ideally, testing at integration before code is entered into production using methods that are as automated as possible. Ideally, doing something that kind of looks like the fuzzing approach that kind of more sophisticated entities are likely to be attempting with your endpoints. One really good test is to just have a set of test credentials for different valid users and see if they're able to access with those test credentials unauthorized content or actions against your products. And then the final piece is refactor. So obviously, fix the authorization flaws to the degree that you know about them, but also very simple steps that you can take to protect yourself in the case of an authorization vulnerability is make sure there are no guessable parameters. Try to avoid incrementing integers, especially global incrementing integers across your products as IDs that are sensitive IDs. You can do a lot to minimize your code and make your client less legible for users so they can have less of the semantic hinting to guide them through the process. And ideally, Alejandro mentioned this in his talk yesterday, there are teams such as Uber who've implemented API gateways that kind of pool together all of their endpoints and allow them to have a much more effective approach for monitoring, authenticating, and also authorizing every request that comes to their products. So I'll stop there. Happy to take any questions. Otherwise, thank you so much for your time.
Mohammed, thank you for a really informative talk. My question is, do you regard these problems as failures in software development and testing? I mean, these are not acts of God or natural phenomena like the weather. These things seem to be problems with the development process itself. It's like if you treat malicious actors as another class of user in your development, and your task is to make their use as difficult and costly as possible, it seems like it would avoid some of these problems. What are your thoughts on that?
100%. Oh yeah, sorry about that. Yeah, absolutely. We have the technology to solve authorization vulnerabilities. This is not something that is a technical issue. And to your point, products that can help mitigate those vulnerabilities at the point of pushing to production, ideally before, would be really valuable. These vulnerabilities simply exist because developers are making up the rules and inspecting the rules. And so if they're failing at doing that correctly, you'll continue to have these types of issues. Formal verification is also just as good as the business logic that someone puts into it. That kind of is the root cause for these vulnerabilities.
So, well, thank you for the presentation. Authentication, authorization, monitoring, everything is good. Everything is must. So let's go one step back. What happens if I, with a simple JavaScript script, send some, let's say, 1 million requests, unauthorized requests to your server, and I still can't get your server down? So what are the strategies there to block such unauthorized requests,
Yeah, I think that's a really good question. If you're a malicious actor, you kind of want to avoid looking like a DDoS attack, because there are really good mitigations at this point against DDoS attacks. You kind of want your footprint to be as minimal as possible. And to identify these vulnerabilities, you might make hundreds or thousands of calls, but you're not going to necessarily appear on the map as ideally, if you're a malicious actor, you're trying to avoid showing up on the map as a real spike on the network. You'll show up at the user level if compared to the average user, but on the overall load on the servers, it's unlikely for you to have a meaningful footprint if you're doing your malicious actor job well.